All right, so this is a lesson on continuity. With continuity, we're going to be specifically talking about continuity at a point and how to prove whether your function is continuous or not at a certain x value. You will talk about functions being continuous or not continuous on intervals or over their whole domain in calculus. That's really why we got to know all of those parent functions so well, so that you can work with those on a bigger scale. But here we're going to be talking about a specific x value. Is a function continuous at x equals 1? Is a function continuous at x equals 5 or x equals negative 5? And in order to do that, we're going to compare the limits at that x value to the actual value. So we're going to be finding the limit and that actual output. If they are the same, if the two-sided limit is the same as the actual output, actual value at that point, f of c here, then your function is continuous at that x value. If it's not, then you prove that it is not continuous at that x value. Now, if you have an exterior point, a point on one of the ends, because a lot of times with these we're looking at piecewise functions. So if we're looking at an end point, then we just do the one-sided limit and the actual value. So that's what this is talking about here, and you'll see some examples of those in the notes. Again, when you get into calculus, you're going to be talking about whole functions on kind of a bigger scale and whether they're continuous over their domain or not. Today, and in this unit, we are really just focused on specific x values. So let's do a couple examples. So, use the function graph to answer the following question. Is f continuous at 1? So what we're going to do with every one of these, and it's going to feel a little repetitive, but you can hang in there. And of course, since this is a video, you can work ahead, pause, whatever, do what you need to do. We're going to compare the left-hand limit. We'll call it A for now. From the left of f of x. We're going to find the right-hand limit. And we're going to find the actual value. And if all of those are the same, then we can say that our function is continuous. If any of those are different, then our function is not continuous. So is f continuous at 1? Well, at 1, here's my value. From the left, we're approaching 3. So the limit as x approaches 1 from the left of f of x is 3. From the right, we're approaching 3. The limit as x approaches 1 from the right of f of x is 3. Excuse me. I don't see a filled-in, well, our filled-in dot anywhere. So f of 1 does not exist. This is how you prove continuity. It is going to seem a little bit repetitious, but these steps are important. So from the left and from the right, that's your two-sided limit is 3. But since f of 1 does not exist, is f continuous at 1? Not continuous. At x equals 1. So you repeated those two column geometry proofs. Now we're kind of working through proving or disproving, and it's going to take a couple steps every time. All right, let's look at a different x value at 2. So at here's 2, x equals 2. Our left-hand and right-hand limit are the same. From the left and from the right, we're both approaching 1. And remember to put that f of x in there. The limit is the actual math that we're doing. So we don't want to say like multiply equals 4. We would have to say the limit as x approaches 2 from the left of f of x, right? That is important. Make sure you're doing the notation correctly. As we think about moving to AP Calculus, that matters. Here we do have a filled in bubble. We do have a point. Our output at 2 is actually 3. So f of 2 is 3. But since it makes that jump, since we have the hole filled in somewhere else, this is also not continuous. All right. Let's work with one that is continuous. Let's prove continuity. So I'm calling this right here 1.6, if that's okay with you. So there, the limit as x approaches 1.6 from the left of f of x. So as we go from the left, we're going to 2. The limit as x approaches 1.6 from the right of f of x. There, we're going to 2 as well. And f of 1.6, there are no holes there that are being filled in somewhere else. It is 2. And since the left hand, the right hand, and the actual output all match, this function is continuous at x equals 1.6. So you've had a couple of different examples here. Now, part A, we had output that did not exist. Part B, we had our limit didn't match our actual ordered pair or our output. Here for part C, we were continuous at 1.6. So let's see what's happening here with D. So we're looking at 3. So here is 3. There's our x equals 3. So from the left, we're approaching 2, right? Again, our limit is about the trend of the graph. If everything kind of went as planned, where is it going? It's not about what's actually happening at the point. It's what is about what's happening as we get really, really, really close. So as we approach 3, our graph is going to 2 from the left. From the right, as we approach 3, our graph is going to 1. So this is the first example where that two-sided limit does not exist. Because the left hand and the right hand limits don't match. Let's go ahead and talk about the actual value, the actual filled in dot there. Our actual output at 3 is 1. So f of 3 is 1. But we can't just have 2 of the 3. We have to have all 3 of our pieces matching. So we are not continuous. At x equals 3. All right, the last example with this picture is an exterior point. So this is how you would work with points like 7 or 3 on this graph, or 0. So when we're looking at an exterior point, this is all the information we're given. This is f of x. F of x just lives between 0 and 7. So as we're working with this, the only information we have is the left-hand limit and the actual point. And that's okay because this is an exterior point. That's all that we're going to compare. So now instead of having 3 things to compare, the left hand, the right hand, and the actual ordered pair, we're going to just compare the left hand limit and the ordered pair. Oops. And if they match, it's continuous. If they don't, then it's it's not. So here, our limit as we approach 7, we're going to estimate a little bit. So, I don't know, I would maybe 1.4. But what I do know is that we are continuous at this point because I have a filled in circle that's at the same place as that as the graph is going. The limit definitely matches there. So this is exterior point continuity. Be true at 0, which is our other exterior point. If we were working with that one, we would just be approaching, we would look at the right hand limit, the limit from the right, and compare that to the actual point. So this is a lot of writing for something that you can kind of get just by inspection, but the proof part of it is important. Being able to write all those steps is very important to what you're going to be doing in calculus. All right. This guy, this picture is, cut right out of a calculus textbook. It's going to step us through a little more, and the whole flow is from a calculus textbook. So it's going to step us through proving continuity instead of just asking us to prove continuity. Does f of -1 exist? So as I look here, this is the crazy piecewise function that we have here. It's probably the most complicated one that we've seen in the unit, but they give us the picture. So we don't have any calculations to do. We just have to look at the picture and use it. So does f of -1 exist? Absolutely. Here is -1. F of -1 is 0. Right? Here's our input, here's our output. Does the limit exist from the right? Well, and the thing to look at here is this guy, this is your exterior point, right? So we're going to only need to do an exterior point continuity here. Does our limit exist here? Absolutely. The limit, as we approach, as x approaches -1 from the right of f of x is 0. Right, the closer and closer we get, we're approaching 0. Does the limit as x approaches -1 from the right of f of x equal f of -1? Well, we just said that the limit was 0 and that the output was 0, so absolutely they match. So is f continuous at -1? It absolutely is. We have exterior point continuity there. The function is not defined to the left of -1. All right, part E, well, now we're talking about 1. X equals 1. So here is x equals 1. I can already tell we're going to be proving that this is not continuous here. So at 1, from the left, we're going to 2. From the right, we're going to 2. But here's our actual ordered pair at 1, 1. So we prove it with all those pieces. The limit as x approaches 1 from the left of f of x is 2. The limit as x approaches 1 from the right of f of x is 2. So the two-sided limit does exist, but it is not the same as the output. F of 1 is 1. So f is not continuous. At x equals 1. All right, a couple more here. And all of these pieces are important. I really am going to discourage you in this part of the unit. Don't skip steps. Do all 3 pieces. And then when you get to calculus, if your calculus teacher or professor identifies a piece that you don't need for their course, you can follow that direction there. Is f defined at x equals 2? Okay, so it's hard to see here, but that is an open circle, and there's no closed circle anywhere else. So f is not defined. F of 2 does not exist. And because of that, we can't be continuous at x equals 2. The limit exists. For the limit from the left and from the right are both 0. But f of 2 does not exist. So it's right on the x-axis there, but since f of 2 does not exist, f is not continuous at x equals 2. Go ahead and pause and do your continuity for 0. Go ahead and pause and get 0 done. I will write it up and review it for you. Okay, hopefully you paused and got that bit done. This one's really interesting. There's no filled in circle anywhere, so f of 0 does not exist. From the left, our limit's -1. From the right, our limit's 0. So here, of course, this is not continuous. Nothing matches at x equals 0. So this idea of continuity at a particular x value is not complicated, but you have to have every piece. You have to be very precise about noting every piece and using that graph or the piecewise function that you're given. There's a couple practice assignments that follow this. The keys are on Canvas. Feel free to ask me any follow-up questions that you need.